Hello guys, this side is Dipali Chandel and I welcome you all over here to Learn AI. So in this particular video, we're gonna cover dimensionality reduction with the help of SVD. Now, a question might popping in your mind, why we want to reduce the dimensions. Okay, let's take the example. This is a document term matrix over here. Now here we have m number of documents, okay, and here out of those documents we have n number of unique words or unique terms. Now as you can see, the length of this document vector, each document vector is n, okay, and the length of each term vector is m. If I want to do some operations on this matrix like classification, similarity or clustering, then that will be little bit complex. Now if I want to make that easy, then we can reduce its dimension, and that dimensionality reduction we can do with the help of SVD, Singular Value Decomposition. Fine. So that clustering, classification and any other operation can become easy. Fine. Now okay, so what is basically SVD is all about? As you can see over here on the screen, SVD theorem. What is SVD theorem? We can break any matrix A into the three matrices. Okay, and this matrix A should be real number matrix. First of all, the condition is matrix A should be real number matrix. That means all the numbers inside the matrix A should be real, not complex. Now, when we decompose this with the help of SVD theorem, then we get a unique set of U, sigma and V matrices. That means we will get only one set of these three matrices that will be the composed part of the matrix A. Now U and V are now known as column orthonormal matrices. Now what I mean by column orthonormal matrices? See, first of all, the transpose of any column orthonormal matrix, the multiplication of that matrix and with its transpose will be identity matrix. So, see, U multiplied by dot product U transpose will be identity matrix. Similarly, V dot V transpose will be identity matrix. Now, what I mean by transpose matrix. So let's suppose U has the dimension x rows cross y column. Now what will be the dimension of U transpose? Y rows x column. That means over here a number of rows become number of columns and number of columns will become number of rows in the transpose matrix. Fine. Now another property of orthonormal matrices are each column in these two matrices, okay, each column in these two matrices, which matrices? U and V, has Euclidean length of 1, means sum of square values in each column is 1. Okay. Another property is if we take any two columns out of U or out of V and we multiply those two columns either from the U or from the V, then what will happen? The dot product of those two columns will be 0. Fine. So these are some properties of orthonormal matrices. Now the sigma over here, the sigma matrix over here, this one, this is known as we can say singular values matrix or singular matrix. Okay, this is a diagonal matrix. What I mean by diagonal, it will has the dimension like same number of rows and same number of columns, x cross x. Okay, and the values on the diagonal will be non-zero and all other values will be 0. Only the values on the diagonal will be non-zero. And one more thing over here, suppose this value is sigma 1, this value is sigma 2 and this value is sigma x, because we have x number of rows and x number of columns. So this sigma 1 will be greater than sigma 2 and so on till sigma x. I hope these properties of these three matrices are clear to you. Fine. Now moving forward. Now let's see how dimensions get decomposed over here. So the dimensions of the matrix A which we want to decompose are m cross n, that means m rows n column. Now the dimension of U that we will get after the decomposition will be m cross r. Now this r will be very small, okay, and the dimension of this sigma matrix will be r cross r, and the dimension of V will be r n cross r. Fine. Now we will use the transpose of it over here. That means this will become V transpose r cross n. Okay, fine. Now this A will be our input data matrix, that which contain m document and n terms. This U will be left singular vectors, okay, which contain m document, and this r is very small in number, which is known as r number of concepts, okay, and sigma is singular values, contain the singular values, and this is we will have the non-zero values on the diagonal, and it tells us the strength of each concept. The concept that we get over here in the U matrix. So this sigma matrix will tell you the strength of each concept. Fine. Now this V is known as right singular vector, which has the dimension n cross r matrix. So n is the number of words, unique words, and r is the number of concepts. Okay, that I already explained. Now moving forward, now suppose over here instead of r, here it is given k. Fine. So don't get confused. Give me a second. Okay. So instead of r, this is just k over here. Okay. This is just k over here. Fine. Okay. So let's see how will it decompose first of all. Okay. Now this is m, this is n, and this will be m. This will have m, and this is k. Okay. Or we can say r. Instead of k, you can take r. Okay. Now this will be r cross r, r number of rows, and r number of columns, or k number of rows, k number of columns. Now this over here, this is V transpose. Okay. So in V transpose, what will be the dimension of V first of all? The dimension of V will be n cross r. Okay. Or n cross k. Now if we do the transpose of it, then we will get k cross n. Fine. So this is k cross n, that means k number of rows and n number of columns in the transpose matrix. Fine. Okay. Now let's suppose for that particular value, for that particular matrix A, the value of k or the value of r is equal to 2. Fine. So here you can see this is first and this is second. Okay. Now so r cross r, that means 2 rows and 2 columns we will get. Okay, this is first row, second row, this is first column, second column, and over here we will get first row, second row, and n number of words. Okay, fine. Now if we decompose it further, so we can write it like this. This is U1 and this is sigma 1. Okay, and this is V1, and this one is VU2. This is sigma 2, singular value, second singular value. Okay, and this is V2. Fine. Now which singular value I'm talking about? We had 2 cross 2 singular matrix. This sigma matrix I'm talking about, 2 cross 2. Fine. So this was sigma 1 and this is sigma 2. Okay. Now the addition of these two, we can say, will give us A. We can decompose that U, V and sigma, U, V, T and sigma in like this as well. Okay. See, you can compare it from here. Fine. Now let's take example over here. Suppose we have 5 movies. Okay. Matrix, Alien, Serenity and Casablanca, Emily. Now these 5 movies we can say are arranged along the columns, and number of users are arranged around the rows. Now each user will give some ranking to each movie. Okay, so this matrix over here denote ranking over here given by each user. So this is user 1. Let's say I am writing it not U, otherwise we will get confused. So yeah, so M1, that is user 1, then M2, user 2. Similarly, how many users we have? Okay, M7. Okay, 7 users we have, and over here we have 5 movies. Now these are ratings for those movies. Okay, now I want to reduce this user to movie matrix with the help of SVD. Okay, now we can decompose it into the U, sigma and VT. Fine. Now let's moving forward further. After decomposition with that SVD theorem, we will get these 3 matrices. Okay, this is my U matrix, this is my sigma matrix, and this is my VT matrix. Fine. Now here are my users, so we can say this is my user. So M cross R is 3. Okay, and this is my R cross R, and this is my because this is VT, V trans, so R cross N. Fine, after the transpose. Now M is number of users and R are number of concepts. So if we see the singular, what I told you, like singular matrix will tell you the strength of each concept inside the U matrix. So which number is maximum over here? This number is maximum, 12.4 out of these 3 numbers. This number is matrix. That means mostly people liked which movie? Mostly people liked this concept, first concept. Okay, fine. Now if we look at these, then we will get these belong to sci-fi concept, these 3, and these 2 belong to romance concept. Okay, and so this first column denote sci-fi concept, and this second column denotes romance concept, and this might be any other concept which SVD decomposed the matrix A into might be some other concept as well along with the sci-fi and romance concept, or we can consider it as noise as well. Fine. Now if we look at the values of the singular matrix, then we will get this number is the highest. That means most of the movies belong to the sci-fi concept. That means the dominant concept out of these 2 concepts is sci-fi concept, or these total 3 concepts is sci-fi concept is the dominant one. Then the second dominant one is romance one. So this is first dominant, then this is second dominant, and we can neglect this 1.3 because it is very less as compared to 12.4 and 9.5. That means we can neglect this one. Similarly over here we can neglect this last row. Okay, in the V transpose. Fine. Now let's move further. This I already explained above. So these numbers, the values, the diagonal values in the singular matrix denote the strength of the concepts. Okay, and these columns denote the concepts. Okay, fine. Now so over here we can see these are our movies. Okay, and these are our concepts. Fine. Yeah, so hold on, this will have R cross N. Yeah, So these are our movies. So this is belong to the Matrix movie, then Alien, then Serenity, then Casablanca and Emily, and these are our concepts. So the most two prevalent concepts are these two, sci-fi and romance. This one is romance concept and the above one is sci-fi concept. Okay, and we can neglect the third one because the number for it is very less, that is 1.3. Fine. Now what we will call this matrix, which is V, we can call it, because over here this is V transpose, right? If we find out the V, V transpose has the dimension R cross N, then what will be the dimension for V? N cross R. So we can say this is, N means movies, right? So V matrix is movie to concept matrix, movie to concept matrix, and this one is user to concept matrix. This U matrix is user to concept matrix, and this is rank matrix. We call it as rank matrix or strength matrix, which will tell us the strength of each concept. Fine. This is for the first concept. This is the strength of the second concept, and this is the strength of the third concept. Fine. Okay. So that I already explained. Okay, so let's take an example over here. In our example, we had 5 movies. Now for the simplicity, I am taking here only 2 movies, movie 1 and movie 2 rating. So the user on the rating of for the movie 1 and movie 2, this is the plot of the user data. Fine. Now we want to find the, suppose instead of 2 axes, I want to plot this data on only 1 axis. Okay. Now how to find that axis? That will be given by the SVD. Let's see that. Okay, moving forward. So over here, now you can see the strength or the variance or spread of the data points around the first concept is quite higher as compared to the second concept and third concept. So by this we get that the projection axis will be along the first concept only. Now these are my concepts. Okay, this was my sci-fi concept, this was my romance concept, and this was some other concept. Okay, so this 12.4 denote my sci-fi concept. So the projection axis, we want to, instead of taking two dimension, I want to just use one projection axis along which I want to distribute my data, you can say. Fine. Now so this axis will be, we will get this axis on the basis of the, on this sci-fi concept vector. Okay, this sci-fi concept vector, because the strength for this concept is quite higher as compared to the below 2 concept, romance and the other one. Fine. Now we got how to find out the projection axis on the basis of the strong concept. Now how to get the coordinate, okay, coordinate points in this new space. What is new space? One projection axis along which we want to find the coordinates for the user data. Okay, now so how to find that? For that we will simply multiply the U and sigma matrices. Okay, and sigma will contain the strength, for each concept, and U will contain the user to concept vectors, or we can say user to concept data over there inside it. Okay, in this one, not user to concept, this will be, yeah, user to concept. Fine. Now so this, when we multiply this U with this we can say sigma matrix, we will get the coordinate points for this projection axis of the user data. So these are the coordinate points of the user data on the projection axis. Fine. That means on the sci-fi axis, coordinate point on the sci-fi axis. Fine. Okay, so how exactly the dimension are getting reduced over here? Now as we see in the singular matrix over here, This is 1.3. So we can neglect this one. So we will neglect this complete, okay, this column and this row. So similarly, over here, this 1.3 denote this concept. So we can neglect this one as well. And this 1.3 denote in this VT matrix this concept. So we can neglect this as well. Now we got two concepts, okay, and this matrix reduced to 2 cross 2 instead of 3 cross 3, and this VT matrix reduced to 2 cross 5, right? Yeah, okay, and this one reduced to 7 cross 2. Okay, fine. So this is how dimensions are getting reduced. Now let's see what we will do furthermore. Now we will set all these, over here we are neglecting them. Okay, this column, this row, and this row, and this row and this column. So we will set all these values to the zeros. Okay, we are neglecting them. Now after multiplication, after multiplying these this matrix, this is U. After we are getting after removing that particular column, and this is singular matrix that we got after reducing this column and this row, and this VT matrix that we got after reducing this after removing this row. Fine. Now when we multiply these three, so we will get, what is the dimension of it? 7 cross 2, 2 cross 2, and this will be 2 cross 5. So when we multiplied, we will get the multiplication of these two will give us 7 cross 2, and then 7 cross 2 multiplied by 2 cross 5, we will get 7 cross 5. Okay, now let's see below. So we will get this matrix over here. Okay, and we will set all the smallest values to the 0. See, so we can see over here, this one, this matrix that we get is approximately equal to the matrix A. This is after reducing the dimension that we got the multiplication of U, sigma and VT, after reducing the dimensions, after reducing those rows and columns corresponding to that particular concept which had very less strength. Okay, this matrix that we got. So this we can see approximately equal to this matrix, because 0.92 is quite closer to 1, then 0.95 is also quite closer to 1. So they are approximately equal. Now this is how we do the dimensionality reduction with the help of the SVD, and this is how all the important information also get retained in our matrix without loss of any information, any important information. Fine. Now I took most of my references from this reference, and from this link, and from this link, and from this channel as well, or artificial intelligence all in one. Fine. Now I hope you guys I'm very clear to you about how we reduce the dimension with the help of the SVD.